So we would like to show the fundamental theorem of arithmetic. According to this theorem, every natural number greater than 1 is either prime or a product of prime numbers in an essentially unique way. So here's a statement. So if n is greater than 1, a natural number, then there exist unique primes P1, P2 up to Pk, such that n first of all P1 is less than or equal to P2, is less than or equal to P3, and so on. It's less than or equal to Pk, and or such that n is equal to P1 times P2, and so on up to Pk. Okay, so the basis of proving something like this comes from a little proposition that needs to be proven separately, according to which if P is a prime number, and P divides the product AB, then P divides A or P divides P. The truth is that in order to prove this, what we need is, so this follows. From the fact that if P does not divide A, then there exists integer numbers X and Y, such that Px plus Ay is equal to 1. Again, in turn, this is pretty much a consequence of a much more general fact that says that if A comma B are integer numbers, then with at least one non-zero, that's a slick way of saying that not both of them can be 0, then there exists integers x comma y such that the greatest common divisor of AB is AX plus BY. So in other words, the greatest common divisor of two numbers is always an integral combination of those two numbers. And now you can see how this should follow, because if P doesn't divide A, then the greatest common divisor of P and A has to be 1, since P is a prime number. And that would mean that there have to be x and y, so that px plus ay is equal to the greatest common divisor of P and A, which is 1. So pretty much the only thing that eventually needs to be proven is this, which is a consequence of the well-ordering axiom. We don't want to dig any deeper into that. We just want to show how this can be used in order to prove the fundamental theorem of arithmetic. So to establish the above statement, one has to show two things: that every number is a product of prime numbers, and that this product is unique. So actually, one could start with uniqueness. So suppose that uniqueness has been established. So it's an inductive argument. So suppose that uniqueness has been established for all numbers less than or equal to k. So every number less than or equal to k can be written in a unique way as a product of prime numbers. Then we would like to show that this is true for k plus 1, because according to our induction principle, the set of all numbers for which the uniqueness holds true will coincide with all the natural numbers. Here, of course, you can notice that there's a small problem with the number 1. So, however, if you modify your statement to say that a number is either 1 or it's a product of prime numbers in a unique way, which is pretty much how the fundamental theorem of arithmetic can be restated, then one can be included in all considerations. So imagine that k plus 1 can be written as a product of prime numbers in two distinct ways, or in two ways, and we will show that the two ways are, so let's say it's p1 up to pk, and it's also equal to q1 up to ql. And here p1 is less than or equal to p2 is less than or equal to pk, and q1 is less than or equal to ql. Actually, I shouldn't have written p2 because we may have just one number. In any case, the idea now is quite simple. By a continuous use of the statement that we gave before, we can show that if a prime number divides the product of a bunch of prime numbers, then it has to coincide with one of them. Okay, let's try to understand why. So if a prime t divides p1 up to pk, then it needs to coincide with one of them. Now, why is this true? So if t does not divide p1, then by applying the statement that we had above, we will have that t has to divide p2 up to pk. And basically, we continue this way, and in the very end, we're going to get that t, either we will find that t divides one of the prime numbers, or we will find that t divides pk. And of course, since both of them are prime, they have to coincide. So by using this, we can claim here that p1 divides q1 up to ql. And this means that it has to coincide with one of these primes. So P1 has to be one of the QIs. And this means that P1 is necessarily greater than or equal to Q1. Now, you can do exactly the same thing with Q1, right? So Q1 divides P1 up to Pk. And so Q1 has to be one of the Pi's, which implies that Q1 has to be greater than or equal to P1. So P1 has to be equal to Q1. And so by dividing both sides, we're going to get P2 equals times Pk equals to Q2 times Qk. And since we divided by a number which is at least 2, these numbers are less than or equal to k. So for these numbers, uniqueness holds, and we will have that we have an equal amount of them, and they have to be equal, and P1 and P2, Q1 were also equal. So the uniqueness has been established for all of the numbers. So now we would have to finish by showing that every number is a product of prime numbers. Every number greater than 1, every natural number greater than 1 is either prime or a product of prime numbers. So the idea here is pretty straightforward. Imagine that there were numbers that were not product of prime numbers. There would have to be a least one of them. So if it is not true that every natural number greater than 1 is either prime or product of prime numbers, then there has to be at least one at least natural number which is neither prime nor product of prime numbers. Let's call this number n. Well, if n is not prime, then it's composite. And it's a product of two natural numbers a and b, which are greater than 1 and less than n. Yes, but we said that it was the least number that was neither a product of primes nor a prime number, which means that a and b are either primes or products of prime numbers. So that tells us right away that n, which is a product of two numbers that are primes or products of prime numbers, is also a product of prime number, and this is a contradiction. So a contradiction comes from what? It comes from the fact that we assumed that it is not true that every natural number greater than 1 is either prime or a product of prime numbers. So it has to be true. And so every natural number greater than 1 is either prime or a product of prime numbers. And we showed before that such a way of writing a natural number as a product of prime numbers is necessarily unique. And that completes the fundamental theorem of algebra. So we can see that in order to obtain the fundamental theorem of algebra, we need to have this little fact about the greatest common divisor. And to establish this fact about the greatest common divisor, we really need to know about the division algorithm. And we need to also use the axiom of the well ordering axiom that every subset of natural numbers has a least element. Every non-empty subset of natural numbers has a least element. I hope that this exposition gave us an idea about how the fundamental theorem of arithmetic is established. Thanks for watching.